Ever wondered how AI crafts images with transparency, like a glass of water refracting light or a semi-transparent logo? Today, we're exploring AlphaVAE, a neural network breakthrough that's rewriting the rules for handling transparent imagery. Let's unpack its architecture, the math behind its success, and why this matters for AI's visual understanding. To grasp AlphaVAE, we first need to understand its foundation, Variational Autoencoders, VAEs. These models act as creative compressors, encoding images into probabilistic latent representations and decoding them back. Traditional VAEs work with RGB channels, red, green, blue, but struggle with alpha channels, the fourth layer that defines transparency. AlphaVAE solves this by extending a pre-trained RGB VAE to process RGBA data, adding a dedicated pathway for transparency. Now let's dive into the math. AlphaVAE employs 4 loss components to refine its transparency handling. 1. Reconstruction loss minimizes pixel-level differences between input and output, but with a twist. For alpha channels, it uses a beta VAE approach, encouraging the model to learn disentangled representations where transparency is independent of color. 2. Perceptual loss compares feature maps from a pre-trained CNN, like VGG, to ensure the AI's output aligns with human perception of realism. For transparency, this involves testing outputs against black, white, and gradient backgrounds to simulate real-world lighting. 3. Regularization loss introduces a KL divergence penalty to keep the latent space structured. This prevents the model from cheating by encoding transparency in the RGB channels instead of the dedicated alpha pathway. 4. GAN loss integrates a discriminator network to enforce realism. The generator, AlphaVAE, must fool the discriminator into believing its transparent outputs are real, pushing it to capture subtle effects like light scattering through semi-transparent materials. The result? AlphaVAE doesn't just generate transparent images, it understands them. By combining these losses, it learns to model transparency as a distinct, controllable variable. For example, when shown a leaf with a translucent edge, the model doesn't just copy the image. It learns how light interacts with the leaf structure, enabling realistic rendering under varying conditions. Benchmark tests show AlphaVAE's superiority. On the realistic transparency dataset, it achieves a 4.86 dB increase in PSNR over prior methods, a leap from blurry to sharp, capturing fine details in alpha channels. The rFID score, a metric measuring perceptual realism, drops by 12.3%, indicating outputs are indistinguishable from real images to human observers. These metrics aren't just numbers. They represent a 30% improvement in usability for designers and 3D artists. Why does this matter? AlphaVAE bridges a critical gap in AI's visual reasoning. It enables tools for photo editing, augmented reality, and even medical imaging, where transparency is key. By treating alpha channels as first-class citizens, it moves us closer to machines that perceive the world with the same nuance as humans. Thanks for watching. If you want to see AlphaVAE in action, check the visuals in the video. Hit subscribe for more deep dives into AI's cutting-edge research, because the future of technology isn't just smart, it's visionary.